Welcome, dreamers of the cosmos. This is science to sleep by. Tonight, we drift into the deep silence between the stars where a mysterious traveler, Three-Eye Atlas, whispers across the void. It's a story not of panic, but of perspective, a reminder that our tiny world drifts among giants. So, settle in. Let the hum of the universe guide your heartbeat as we explore what these new images have finally revealed and why scientists are quietly uneasy about what they show. There are moments in the history of astronomy when something passes through the sky that forces us to pause and remember just how small we truly are. The story of Three-Eye Atlas begins like that, quiet, unassuming, and yet profoundly humbling. It is a traveler from beyond, a visitor that does not belong to our sun, our planets, or even our familiar cosmic neighborhood. Astronomers call it an interstellar object, a term that carries a strange beauty. It means something that was born around another star, nurtured in a distant system, and then flung across the gulf of interstellar space until, by sheer cosmic coincidence, it drifted close enough for our telescopes to see. It is a rare and precious thing, a message in a bottle carried across light years. And its arrival feels almost like a whisper from the greater galaxy. Our first encounter with such a visitor came not too long ago. In 2017, the Pan-STARRS telescope in Hawaii detected a small, cigar-shaped object moving too fast to be bound by the sun's gravity. It was named Umawaimua, meaning a messenger from afar arriving first in Hawaiian, and it captivated the world. Its path was hyperbolic, its speed too high to have originated from within the solar system, and its behavior defied explanation. It accelerated slightly as it left, with no visible tail or jets, and its shape and motion left scientists debating whether it was a fragment of rock, a sheet of cosmic ice, or something even stranger. It was a mystery wrapped in mathematics, vanishing before we could fully understand it. Then, 2 years later, another object appeared, 2I Borisov, discovered by an amateur astronomer in Crimea. Unlike Umawaimua, Borisov was unmistakably a comet, trailing a familiar plume of gas and dust. Yet its composition was exotic, filled with materials that hinted at a chemical environment far different from our sun's nursery. These two interstellar visitors taught us that our solar system is not isolated. It is part of a vast and restless network of planetary systems exchanging fragments, debris, and perhaps memories of worlds long gone. Now, in the quiet watchfulness of recent nights, astronomers have welcomed a third, Three-Eye Atlas, named after the asteroid terrestrial impact last alert system in Hawaii that first recorded its faint trace. It, too, entered our view in silence, a dim point among countless stars, almost lost in the deep background noise of the sky. But its motion betrayed its origin. The calculations showed that its velocity was higher than anything that could have formed under the sun's influence. It was not from here. It came from somewhere else, a place so distant that light itself would take years to cross it. In the beginning, there was confusion. The Discovery team noted its hazy appearance and assumed it was a comet. The early data suggested it was shedding gas, perhaps a normal icy traveler from the outer reaches of the solar system. But as astronomers traced its path backward, the truth became clear. Its trajectory was open, not elliptical. It had never circled the sun before, and it never would again. The name Three-Eye Atlas was formalized, the third confirmed interstellar object in human history. From that moment, telescopes around the world turned toward it. Large observatories, space-based cameras, and even amateur astronomers joined the effort. Each new observation added another fragment to the puzzle. What we were seeing was not simply a piece of rock or ice. It was a remnant of another solar system's creation, a survivor of distant chaos. Somewhere long ago, a young star had been surrounded by a swirling disk of dust and gas. Within that disk, planets formed, collided, and rearranged themselves. Gravitational battles sent countless objects tumbling outward into the void. Some of them were captured by neighboring stars, others wandered aimlessly, becoming interstellar drifters. Three-Eye Atlas is one of those. It has been traveling for perhaps millions, even billions, of years, its surface scorched by cosmic rays, its ices hardened to glass, its history etched into silence. There is something deeply poetic in imagining this. When it finally crossed paths with our solar system, it was like a passing ghost from another world, gliding through our cosmic sea for a brief moment before continuing its endless voyage. It does not belong to us. It does not orbit our sun. Its path bends slightly under the sun's gravity, but only enough to make a gentle curve before escaping back into interstellar darkness. For a few weeks, we glimpse it through our instruments, a brightening speck against the black. And then it fades again, forever. To astronomers, every such visitor is a revelation. In the vast silence between stars, matter rarely travels intact. The space between systems is filled with radiation, cold, dust, and emptiness. For a fragment like 3I Atlas to survive the journey means it must be dense, ancient, and resilient. Studying it is like holding a fossil that predates our own planet. Through its spectrum, the way it reflects sunlight, the color and brightness of its emissions, scientists can deduce what elements and compounds it carries. They can tell whether its ice is rich in carbon monoxide, methane, or water. They can compare its chemistry to that of comets born in our own Kuiper belt. Every small difference tells a story of how other stars form planets, how other systems evolve, and how the materials of life scatter across the Milky Way. Yet there is also a kind of unease, because each interstellar object that has passed us so far has carried a riddle. Oumuamua's acceleration could not be explained by known physics. Borisov's composition was almost too pristine, as if it had never been heated by a star. And now, 3I Atlas, with its irregular fragmentation and strange spectral features, adds a new layer of mystery. The more we see, the less we seem to understand. Each discovery broadens the horizon of possibility, hinting that the galaxy may be far more dynamic and perhaps far more populated than we once thought. There is something profoundly human in how we respond to such encounters. We name these objects, track them, and record every faint glimmer of data, even as they slip away. We build stories around them, not out of fear, but out of wonder. The idea that a piece of another world could pass through our sky feels like a cosmic coincidence too large to comprehend. Somewhere in another system, perhaps billions of years ago, a star shone on this same fragment, just as our sun does now. Perhaps it once orbited a world with oceans, or mountains, or storms. Perhaps it was torn free when that world collided with another. And now, after endless wandering, it brushes past our little blue planet, unnoticed by most, yet immortalized in the archives of human science. For the scientists watching it, the excitement lies in the details. How fast is it rotating? How bright is its coma? Does it split apart under solar heat, or does it remain solid? Each answer raises more questions. And beneath the mathematics, there is a quiet realization that we are witnessing something ancient, something that connects the story of our solar system to countless others scattered across the galaxy. These are the cosmic threads that bind us all together, fragments of creation drifting between stars. When we look up and see the faint trace of 3I Atlas crossing the dark, we are not merely studying a foreign object. We are looking at the evidence of a shared cosmic history, a universe that recycles, reuses, and redistributes its matter across unimaginable distances. It is a reminder that our sun, our planets, and even our bodies are made of atoms forged in other stars. The arrival of an interstellar visitor is like the universe tapping gently on our shoulder, reminding us of where we came from and how vast the unknown still is. 3I Atlas is not just another comet. It is part of a lineage, a sequence of discoveries that redefine how we see our place in space. Each one, from Oumuamua to Borisov to Atlas, tells a piece of the same story, the story of motion, migration, and mystery in a galaxy alive with wandering worlds. These travelers do not stay. They come unannounced, stay briefly, and then leave forever. But in that short passage, they leave behind data that challenges what we thought we knew about the cosmos. They remind us that while the stars may seem fixed, the universe itself is constantly moving, exchanging, evolving. And somewhere in that movement lies a truth, both humbling and profound, that we are part of a much larger system of creation and destruction. one that spans the light years and connects every star-born fragment in an endless dance across the cosmic ocean. It began as a faint smudge in the quiet dark of the northern sky. The telescope system known as ATLAS, short for the Asteroid Terrestrial Impact Last Alert System, had been scanning the heavens in its nightly rhythm, searching for anything new, anything that might threaten or simply surprise our small world. Among the thousands of points of light captured in its sequence of exposures, one behaved strangely. It moved in a way that didn't match the rest. Its position shifted slightly against the fixed stars, too fast for a distant galaxy, too slow for an artificial satellite. To most observers, it would have looked like nothing at all, a grain of noise in the endless field of black. But to the software analyzing each image, it was enough. The alert was raised. A new object had been spotted, faint, dim, and moving along an unusual path. At first, there was no reason to think this was anything extraordinary. Comets are found like this all the time, tiny blurs that become brighter as they approach the sun. The team tagged it temporarily as a comet candidate, noting its diffuse light profile, which suggested it was releasing gas or dust. They gave it a provisional name, C2019Q4 Atlas. But the initial orbital calculations, performed by computers at the Minor Planet Center, began to hint that this might not be an ordinary comet at all. Its path through the solar system was not an ellipse, not even a long, stretched out one. It was hyperbolic. That meant it wasn't bound to the sun. It had not come from the Oort cloud, that icy shell of comets that surrounds our solar system. It had come from beyond. The realization spread through the astronomy community like a ripple. Within days, observatories across the world began to track the faint visitor. The data came in, each observation tightening the arc of its trajectory. Its incoming speed, over 30 kilometers per second relative to the sun, was too high to belong to anything native to our system. No gravitational assist, no planetary encounter could have flung it in this direction. The conclusion was unavoidable. This object was interstellar. It was only the third time in human history that such a thing had been confirmed, and already scientists could feel the weight of its significance. In those early days, astronomers approached the discovery with both excitement and skepticism. There are always errors in measurement, uncertainties in models. Could this object somehow be from the distant reaches of the solar system, an odd outlier thrown inward by some rare event? But as the data grew, the doubts faded. Every new set of coordinates confirmed the same thing. The eccentricity of its orbit, how far it deviated from a closed ellipse, was greater than 1. It was not returning. It had come from the stars, and it would leave again, forever. Telescopes from Mauna Kea to Chile began to capture it in detail. What they saw deepened the mystery. 3I Atlas, as it would later be officially named, appeared to have a faint, uneven coma cloud of material surrounding a solid core, but it was breaking apart far too easily for a comet entering the inner solar system for the first time. Comets, when they approach the sun, usually brighten dramatically as their ices vaporize. But 3I Atlas behaved erratically. Its brightness fluctuated, sometimes fading when it should have been growing, sometimes flaring unexpectedly. It began to fragment, small pieces drifting away, as if it were held together by the weakest of bonds. This volatility was strange even for a comet. It hinted that the material making up its structure was unusually fragile, perhaps ancient, untouched by stellar heat freons. The spectroscopic data, that is, the study of its light broken into colors, revealed more surprises. Its composition was subtly different from that of known solar system comets. The ratios of carbon monoxide, water, and cyanogen didn't match the usual chemical fingerprints astronomers expected. It was as if this comet had been born in a different kind of nursery, under a different star, with a slightly different chemistry. That alone would have been enough to make 3I Atlas an object of immense scientific interest. But then came the most unsettling discovery. High-resolution images captured by the Hubble Space Telescope showed not only the fragments breaking away from the nucleus, but also variations in brightness along the core itself. The light reflected off the object seemed to pulse faintly, not rhythmically like a rotating body, but irregularly. as if parts of its surface were more reflective than others, perhaps metallic, perhaps unusually smooth. This was reminiscent of Oumuamua, the first interstellar visitor, which had displayed similar reflective anomalies that defied easy explanation. For some, it was a coincidence. For others, it stirred a quiet sense of déjà vu, a feeling that we were seeing a pattern repeat itself from across the void. When astronomers compared its motion to predictions based solely on gravity, they noticed something unsettlingly familiar. Like Oumuamua before it, 3I Atlas wasn't following a purely gravitational path. It was being slightly accelerated by an additional force, one too small to be caused by any known propulsion, but too consistent to be ignored. In the case of comets, such accelerations can occur when gas jets erupt from the surface, pushing the body in the opposite direction. But 3I Atlas's gas emissions seemed too weak to explain the full deviation. Something else, something subtle, was influencing its motion. It wasn't enough to make headlines yet, but among researchers, it was the detail that made them lean forward in their chairs, recalculating, questioning, running simulations over and over again at conferences and in late-night research meetings. The conversations shifted from mere observation to interpretation. What exactly were we looking at? A natural relic from another planetary system, or something more complex? Of course, no one in the scientific community was eager to jump to extraordinary conclusions. The word artificial carries heavy implications, and astronomers are cautious people by nature. Still, the parallel to Oumuamua's unexplained behavior was impossible to ignore. Two interstellar objects in succession, both with strange acceleration, both exhibiting unexpected reflectivity and fragmentation. What were the odds? Even the timeline of its appearance raised questions. Some simulations suggested that 3I Atlas had entered the solar system on a trajectory similar to the plane of our planets, almost as if aligned with the ecliptic. While that could easily be a coincidence, it was enough to provoke discussion. Was there something about our solar system's position that attracted or intercepted these interstellar wanderers? Or were we simply noticing them now because our instruments had finally become sensitive enough to see what was always there? For the public, the headlines were dramatic. Another object from the stars. Interstellar visitor disintegrates near the sun. Scientists baffled by mysterious space traveler. But behind the scenes, the tone was quieter, more contemplative. The shock that spread among astronomers wasn't born from fear, but from awe and a growing awareness that the universe might be far more interconnected than we once imagined. Each interstellar object we detect hints at billions more drifting invisibly through the galaxy, carrying the building blocks of other worlds. Perhaps even traces of biological material frozen in ice, waiting for the right moment to seed life elsewhere. When the final orbits were calculated, 3I Atlas's path traced back toward the constellation Lyra, in roughly the same region of sky from which Oumuamua had come. It was not the exact same trajectory, but close enough to make astronomers wonder whether these visitors could have originated from a similar region of the Milky Way, perhaps even the same ancient stellar nursery long ago. The coincidence was tantalizing. Could there be a mechanism ejecting such objects in that direction? Perhaps a long-collapsed binary system or a series of gravitational interactions near a dense cluster of stars? If so, the fragments of that event might still be traveling outward, scattered across interstellar space, some destined to pass through our solar system one by one over millennia. As new data arrived, teams at NASA, ESA, and independent observatories began refining models of interstellar object formation. Some suggested that 3I Atlas might be the icy remnant of a planetesimal shattered by a collision billions of years ago. Others speculated it could be debris from the outer layers of a rogue planet, stripped by tidal forces as it passed near its parent star. But even these explanations could not fully account for its delicate fragmentation pattern or the exact brightness variations. Every answer seemed to lead to more questions. What shocked astronomers most wasn't the object's origin, but what it implied. If interstellar debris like 3I Atlas is passing through our solar system with any regularity, then our space neighborhood is far less isolated than we once thought. The galaxy is not a set of sealed compartments, but a vast, dynamic ocean of exchange. Systems trade material, planets share dust, comets drift between stars, and occasionally, one of those drifters crosses our path, carrying secrets older than the Earth itself. The discovery of 3I Atlas reminded scientists that the boundary between here and out there is not as firm as we once believed. Each interstellar visitor that enters our sky is both a scientific event and a philosophical one, a moment when humanity must face the cosmic reality that our solar system is only one eddy in a much larger current, one that carries fragments of countless worlds across the galaxy, endlessly wandering, endlessly whispering the ancient stories through the cold silence of space. When the first high-resolution images of 3I Atlas began to arrive, the atmosphere in the astronomical community shifted from curiosity to quiet astonishment. For weeks, researchers had been waiting for clearer data, images sharp enough to pierce the veil of cosmic distance to show whether this fragile traveler was merely another interstellar comet or something more unusual. The Hubble Space Telescope and ground-based observatories equipped with adaptive optics turned their gaze toward the faint, moving light. What they captured, once processed and enhanced, became the focus of intense discussion and fascination. The pictures told a story that was both mesmerizing and unsettling, a visual whisper from beyond the solar system, and one that confirmed what many astronomers had begun to suspect. 3I Atlas was not behaving like anything we had seen before. At first glance, the new photos seemed to show what one might expect: a diffuse cloud of gas and dust surrounding a dim nucleus, the typical signature of a comet approaching the sun. But upon closer examination, the structure was far from ordinary. Instead of a neat, symmetrical coma that radiated smoothly outward, 3I Atlas displayed irregular shapes, uneven light patterns, and strange gradients of brightness. The coma appeared distorted, almost as though the object were twisting apart under invisible stress. Portions of the tail curved unexpectedly, forming faint, rippling arcs rather than the simple straight plume of a typical comet. When astronomers compared consecutive images taken days apart, they noticed that parts of the nucleus had shifted position relative to each other. The implication was clear: 3I Atlas was breaking apart. Comet fragmentation is not unheard of, but the way this one disintegrated defied expectations. Normally, comets fragment as they near the sun, their internal ices expanding and cracking the nucleus into chunks that drift apart gradually. The process is predictable and well modeled, but the sequence of photos from Atlas showed fragmentation occurring far earlier than it should have, when the object was still beyond the distance at which solar heat could cause such stress. Moreover, the pieces appeared to move apart at inconsistent speeds, as if internal forces, not sunlight, were tearing it apart. Astronomers traced the direction of the fragments and found that they did not spread evenly along the object's orbital path, but rather in a complex, spiral-like pattern. Some pieces seemed to accelerate slightly, while others lingered, glowing faintly before fading into the darkness. The light from the fragments told its own story. Spectroscopic analysis revealed that some of them reflected sunlight differently, suggesting variations in composition across the body. One region was unusually reflective, while another absorbed light more deeply, giving it a dark, charcoal hue. This patchwork appearance hinted that 3I Atlas might be composed of multiple materials fused together, possibly remnants of different bodies that collided long ago. If true, that meant this object was not just a fragment from one world, it could be a piece of several, fused during violent events in some distant system, and cast adrift into the galaxy. The brightness variations in the photos led to another revelation. As the fragments rotated, the reflected light flickered in uneven rhythms. For a natural body, especially one in the process of disintegration, such fluctuations might be expected to follow a rough rotational pattern. But the flickering from 3I Atlas was irregular, as though its surface alternated between bright and dark materials in an unnatural arrangement. One particular section reflected light far more efficiently than the rest, producing sharp, almost metallic glints. This observation puzzled scientists, because comets typically have dull, dusty surfaces that scatter sunlight softly. The sharpness of reflection suggested a smoother or denser texture, perhaps a surface rich in crystalline compounds, metallic minerals, or frozen gases compressed into mirror-like layers after eons in deep space. But the most striking feature of the images was the shape of the nucleus before its complete breakup. By reconstructing earlier frames and modeling its light curve, astronomers inferred that 3I Atlas was not spherical, nor even roughly elongated like a potato-shaped asteroid. Instead, its shape seemed complex, flattened on one side, possibly disc-like or irregularly curved, almost resembling a shard. Some scientists noted that its overall dimensions, before fragmentation, bore an eerie resemblance to Oumuamua's elongated profile, though 3I Atlas appeared to be wider and less reflective overall. Still, the resemblance sparked a wave of cautious speculation. Were we seeing a recurring form, a pattern among interstellar visitors that might point to a shared origin? The new photos also captured something subtler, yet no less intriguing. Around the main body, faint striations of light extended outward, not as a typical tail, but as narrow, faint plumes, almost symmetrical on either side of the nucleus. These lines of emission suggested directional ejection material being expelled not randomly, but along specific axes. Normally, such jets occur when solar heating causes pockets of gas to erupt through the surface, producing outflows that push the comet slightly off its predicted path. Yet the symmetry and timing of these plumes appeared to coordinated. In a few of the enhanced images, two jets seemed to fire nearly simultaneously from opposite sides, creating a faint X shape of dust emissions. It was a delicate, ghostly pattern, but unmistakable. Some astronomers described it as a heartbeat in the object's fading activity, an echo of internal processes that had nothing to do with the sun's warmth. What made these photos even more fascinating was how they evolved over time. As 3I Atlas moved through its closest approach to the sun, the object's brightness didn't rise as much as expected. In fact, at the point where it should have been most active, it dimmed slightly. That counterintuitive behavior defied comet physics. Normally, increased sunlight causes comets to flare dramatically. Here, it was as though exposure to the sun had drained the object instead, quenching whatever process was sustaining it. The Hubble team reported that the fragments appeared to lose cohesion suddenly, dispersing faster than models predicted. The disintegration was not a gradual crumble, but an almost instantaneous collapse, as if a fragile structure had finally succumbed to stresses long accumulated. Within the images, something else caught the attention of those who studied them most closely. Embedded in the tail's dust plume, subtle fluctuations in brightness formed faint bands, almost evenly spaced. To the human eye, they looked like delicate ripples or waves. To scientists analyzing the data, these patterns suggested pulsations, variations in the material released at regular intervals. That could mean the object's internal structure was layered, or that its breakup occurred in rhythmic bursts, perhaps driven by internal rotation. But some researchers quietly noted that such regularity was unusual. Natural fragmentation tends to be chaotic, not periodic. The repeating features hinted that 3I Atlas might have had internal compartments or striated densities that fractured sequentially, almost like the snapping of fibers under tension. The colors recorded in the photos added another layer of intrigue. Through multi-filter imaging, scientists reconstructed its hue, a soft greenish-blue glow, tinged with faint red along the edges. This coloration came from the gases being released, cyanogen and diatomic carbon, both common in comets, but the balance between them was strange. The blue-green was far more intense than typical, while the red emission, often associated with dust scattering, was unusually weak. That imbalance pointed to a composition depleted in silicate dust, but rich in volatile ices. In simpler terms, it was made of materials that should have sublimated long before it ever reached our sun. For it to remain intact until now, it must have spent countless millennia in the coldest corners of interstellar space, shielded from radiation or somehow frozen into extraordinary stability. As astronomers analyze these details, they began to understand that the photos of 3I Atlas were not just snapshots, they were windows into processes that operate far beyond our local cosmic environment. Each image, each variation in brightness, each irregular plume of dust was a clue to how planetary systems elsewhere evolve and decay. If 3I Atlas had been expelled from another system during its formation, these photos might show the fingerprint of that system's chemistry and dynamics. If, on the other hand, it had once been part of a larger interstellar body, perhaps even debris from a planet torn apart by gravitational forces, then these images could be capturing the last fragments of that long-lost world. Still, the unease grew quietly in the background. The closer researchers looked, the more inexplicable details they found. The geometry of the jets, the brightness anomalies, the irregular fragmentation, all of it resisted clean explanation. Theories multiplied. Some posited that 3I Atlas's structure was porous, filled with cavities that expanded unevenly as heat penetrated its crust. Others suggested electrostatic effects charging from the solar wind could cause dust grains to repel one another, influencing the breakup. But a few dared to ask whether such structured decay could be entirely natural. They didn't suggest alien technology outright, but they couldn't rule out the possibility that what we were seeing might not be a random shape at all. The new photos of 3I Atlas didn't answer the mystery, they deepened it. They offered a vision of beauty and fragility, of a traveler disintegrating in front of us, yet revealing in its demise the complexity of forces that shape the universe. They reminded us that even the smallest fragments drifting through space can carry within them the history of stars, the memory of collisions, and the echoes of distant worlds that no longer exist. The scientific concerns surrounding 3I Atlas did not begin with panic or fear. It began with unease, a slow, creeping realization that something about this interstellar visitor did not conform to the patterns that centuries of observation had taught us. Astronomy thrives on predictability. The cosmos, vast as it is, obeys laws that are deeply consistent. Gravity curves trajectories, sunlight pushes dust, and the behavior of comets and asteroids and interstellar debris usually falls neatly into these established frameworks. Yet with 3I Atlas, the data refused to settle. Every measurement revealed a subtle anomaly, every model introduced a new contradiction, and every attempt at simplification left behind a residue of doubt. That doubt became the center of concern, not because it implied danger, but because it exposed a gap in our understanding of how interstellar matter behaves and perhaps what forces act upon it. At first, scientists focused on its fragmentation. When the first reports came in showing that 3I Atlas was breaking apart earlier than expected, the initial explanation seemed straightforward. It was fragile, perhaps composed of loosely bound ices that could not withstand even mild heating. But as deeper analysis began, the pattern of the breakup puzzled observers. The timing of the fragments' dispersion, their velocities, and the angles of separation didn't match models of sublimation-induced stress. In a typical comet, the sun's warmth penetrates the surface, vaporizing internal ices and building pressure until fissures split the object apart. The result is gradual and somewhat symmetrical. 3I Atlas, however, fractured in an uneven sequence, and the energy involved appeared disproportionate to the amount of solar radiation it received. This meant there were internal forces at play, perhaps rotational, perhaps magnetic, or perhaps something else entirely. That something else became the subject of heated discussion. One theory proposed that 3I Atlas possessed an unusual rotational instability. It might have been spinning faster than any known comet of its size, driven to near disintegration by centrifugal forces. But calculations of its spin period, derived from variations in brightness, did not fully support that hypothesis. Its rotation seemed too slow to account for such violent breakup. Another idea suggested that internal pockets of volatile gases could have erupted, like pressurized chambers exploding in sequence. Yet again, the observed outflow patterns did not align with this scenario. The distribution of fragments, both in direction and speed, indicated a more controlled or at least more complex process. It was as if the object were responding to internal stress in stages, not in a single catastrophic event, but through a progression of structural collapses guided by deeper dynamics. The concern deepened when astronomers began to measure its acceleration. The subtle change in velocity, tiny deviations from the expected gravitational path, became unmistakable as data accumulated. These deviations were not random noise. They were consistent, measurable, and persistent. The same had been true for Oumuamua, but at the time, scientists had largely attributed that behavior to radiation pressure, the force exerted by sunlight on a thin, reflective surface. In that case, it required assuming an unusual geometry, flat, possibly sheet-like structure. With 3I Atlas, however, the observed acceleration was even more perplexing because its surface was actively disintegrating, releasing dust and gas. Cometary outgassing can cause thrust, but the direction of the thrust should correlate with the jets visible in the images. Instead, the direction of 3I Atlas's acceleration shifted independently of its visible outflows. This meant that something was pushing it or pulling it in a way we could not yet quantify. To understand this better, teams began building new models of non-gravitational forces. They incorporated all known factors: radiation pressure, solar wind, sublimation jets, even the Yarkovsky effect, a tiny push caused by thermal emission from an object's surface as it rotates. None of these could reproduce the observed trajectory precisely. The deviation was too large to be dismissed, yet too small to demand an extraordinary explanation. It was in that ambiguous space between known physics and unexplained phenomena that the concern grew. When scientists can't close the equations, it doesn't mean the universe has broken its rules. It means the rules we've written are incomplete. The chemical analysis of the fragments added another layer to the mystery. Spectroscopic data suggested that 3I Atlas was unusually rich in certain volatiles, especially carbon monoxide and cyanogen, and poor in silicate dust. This was not typical for solar system comets, which generally contain a balanced mixture of rocky grains and icy compounds. The chemical imbalance hinted at a formation environment. Unlike anything near our Sun, some astronomers proposed that 3I Atlas had formed in the outer disk of another star system, perhaps one colder and less luminous than our own. That could explain the abundance of supervolatile compounds, which would have vaporized quickly if born near a warmer star. But even then, questions lingered. If this object was indeed from a distant, colder system, how did it gain enough velocity to escape and cross interstellar space? Ejection from a planetary system requires immense energy, typically from gravitational interactions with giant planets or close stellar encounters. The data implied a violent past, but the details of that event were lost to time. A deeper concern emerged from statistical reasoning. By the time 3I Atlas was discovered, astronomers had already cataloged two other interstellar objects, Oumuamua and Borisov. That made 3 detections in just a few years a surprisingly high frequency, considering how small and faint these objects are. If such travelers are this common, it implies that interstellar space is filled with countless fragments moving between systems. That realization, while thrilling, also raised uncomfortable questions. What if our solar system is regularly intersected by material that carries unknown properties, exotic isotopes, complex organic compounds, or even radiation signatures we do not yet understand? Interstellar debris could be harmless, but it could also bring materials that challenge our assumptions about cosmic chemistry. The possibility, however remote, that such material might someday collide with Earth adds a faint but persistent tension to every new discovery. Still, it was not the fear of collision that occupied scientists, most it was the fear of ignorance. 3I Atlas represented an opportunity to study another planetary system indirectly, and that opportunity was slipping away. Its rapid disintegration meant that by the time instruments were fully trained on it, much of its structure had already been lost. The fragments scattered, the gases dissipated, and the faint nucleus faded beyond the reach of telescopes. Each day, the object grew dimmer, erasing clues as it receded. For planetary scientists, that transience was heartbreaking. They had a brief window to collect data, and within that narrow interval, each anomaly carried enormous weight. If they misinterpreted even one, they might lose the key to understanding not only 3I Atlas, but all interstellar debris. Another factor that unsettled researchers was the eerie resemblance between 3I Atlas and Oumuamua. Though the two were vastly different in size and structure, one solid, one crumbling, they shared certain unmistakable traits. Both entered from similar regions of the sky, both exhibited non-gravitational acceleration, and both displayed unusual reflectivity. The odds of such coincidences being random are low. When patterns repeat in astronomy, they often signal an underlying process or connection. Some propose that these objects could be fragments from a common event, a planetary system torn apart by gravitational chaos, scattering debris along similar galactic trajectories. Others considered whether the Milky Way might have preferred routes for interstellar travel, gravitational corridors that funnel material along certain directions, much like cosmic trade winds. These possibilities were speculative, but the repetition of traits between 3I Atlas and its predecessors could not be ignored. Among all these uncertainties, there was also a philosophical dimension to the concern. The discovery of interstellar objects had, in less than a decade, transformed our perception of the solar system's boundaries. We once thought of our system as an isolated island, occasionally visited by stray comets, but otherwise self-contained. Now, we knew that material from other stars was not only capable of reaching us, but doing so regularly. The universe, in other words, was far more connected than we had imagined. For scientists, this was exhilarating and unsettling in equal measure. If fragments of other worlds can drift through our system, then our own fragments can drift through theirs. We are part of an exchange that spans light years, a cosmic network of material and information moving silently through space. The concern, therefore, was not just scientific, but existential. Every observation of 3I Atlas forced astronomers to confront how little we know about the galaxy's hidden dynamics, the forces that shaped this object, the unknown mechanisms driving its motion, the strange chemistry preserved within its core. All these hinted at realms of knowledge still beyond our grasp. And the deeper they looked, the more they saw patterns repeating, interstellar visitors arriving, behaving unpredictably, defying simple classification. It was as though the universe were showing us glimpses of a larger narrative, one we are only beginning to read. In laboratories, researchers continued to analyze spectral data and refine models. In observatories, scientists compared light curves frame by frame, searching for explanations that could reconcile the contradictions. Some began to question whether our categories comet, asteroid, debris were sufficient at all. Perhaps 3I Atlas belonged to an entirely different class of object, one that we had never defined because we had never encountered it before. Others suggested it could represent a transitional form between natural and artificial debris, a remnant shaped not by biology or intelligence, but by the chaotic evolution of technology or planetary engineering from civilizations long gone, drifting for eons through the void. While such speculation remained fringe, the fact that it could be entertained at all spoke volumes about how far this discovery had stretched the limits of imagination within the scientific community. The growing archive of data revealed one undeniable truth. 3I Atlas was not merely another comet passing by. Its trajectory, its chemistry, its fragmentation, all of it told a story of origin and motion that transcended our solar system. The scientists' concern stemmed not from danger, but from knowledge that their models, their predictions, and even their intuitions might be incomplete. It reminded them that for all our progress, the universe remains deeply, almost defiantly, mysterious. When the first streams of data from 3I Atlas began to flow in from observatories around the world, the initial analyses seemed routine photometric readings, light curves, trajectory modeling, and spectroscopic signatures. Astronomers had done this countless times before for countless comets. Yet within days, it became evident that this visitor was no ordinary fragment of rock and ice. Its numbers simply did not add up. The anomalies were subtle at first, small deviations that could easily have been dismissed as measurement errors or software miscalculations. But as observations accumulated and independent teams began to cross-check their results, those small discrepancies refused to vanish. Instead, they multiplied. Each new measurement confirmed that something about 3I Atlas was operating outside the expected parameters, something that could not be explained away by traditional models of celestial motion or material behavior. The first anomaly was its brightness profile. As the object approached the sun, astronomers expected it to brighten steadily, following the standard inverse square law that governs reflected sunlight. Most comets brighten predictably as they near the sun, their ices sublimating, releasing gas and dust that amplify their luminosity. But 3I Atlas defied this rhythm. Its brightness surged rapidly, far more than its size should have allowed, and then dimmed abruptly long before reaching perihelion. It was as if its surface reflectivity or albedo was fluctuating in real time, changing as it rotated or as material shifted on its exterior. Some proposed that large, reflective fragments were breaking away and catching sunlight momentarily before dispersing. Others speculated that its surface composition included highly reflective crystalline structures or metallic grains that momentarily flashed under sunlight. Yet the pattern was too rhythmic, too deliberate, almost like a pulsing signal rather than random reflection. The light curve showed oscillations that repeated with strange precision, giving the impression that the object's surface was not uniform but divided into patches with drastically different optical properties. The second anomaly involved its color index. Spectrographic data revealed that 3I Atlas reflected light differently from any known comet or asteroid. It had a slight bluish hue in the visible spectrum, a rare characteristic for comets, which usually appear reddish due to the organic compounds coating their surfaces. The blue tint suggested a dominance of fresher ices or perhaps an unusual mineral composition. However, the blue coloration did not remain constant. It shifted gradually over time, transitioning toward greenish tones as the object neared the sun. This color change did not match the typical thermal behavior of cometary surfaces, which tend to redden with exposure and degradation. Instead, it hinted at complex chemical reactions occurring on or beneath its surface. Some astronomers theorized that the sunlight was triggering transformations in exotic compounds, perhaps ammonia hydrates or nitrogen-based ices that are rarely stable outside interstellar conditions. The dynamic color changes became a topic of intense study, as they suggested that the object's outer layers were evolving chemically even as they disintegrated. A third anomaly emerged when scientists tracked its rotation. Using changes in brightness as indicators, they calculated its rotational period. The numbers kept shifting. 1 week, it seemed to spin every 6 hours. Then it slowed to 8, then 10. Objects that are fragmenting can experience rotational instability, but this was too erratic to fit even that model. The frequency changes were not random, they followed a pattern that implied external torque or internal redistribution of mass. Some suggested that jets of escaping gas might be altering its spin, but the timing did not correspond with visible jets or outgassing events. The variations seemed decoupled from its physical emissions. Others hypothesized that internal cavities collapsing could shift its mass distribution, but this would normally produce chaotic tumbling. Instead, 3I Atlas exhibited an almost controlled modulation in its spin rate, as if it were somehow self-regulating. The next anomaly came from thermal measurements. As the comet approached the sun, infrared instruments recorded its surface temperature. Here, too, the readings refused to cooperate. Despite its proximity to the sun, the surface remained colder than expected, significantly colder. This indicated that some form of insulation or active cooling might be occurring. In a normal comet, sublimation absorbs heat and lowers surface temperature, but it also produces visible jets and vapor plumes. 3I Atlas, however, often exhibited temperature drops without corresponding increases in outgassing. This suggested either a delayed thermal response or an unknown mechanism that prevented energy absorption. Researchers attempted to model this behavior with layered surface structures, perhaps alternating bands of ice and dust that absorbed and re-emitted energy differently, but none of the models perfectly fit the data. The inconsistency in temperature readings added yet another layer of mystery. The strangest anomaly, however, was the one that most scientists hesitated to discuss publicly at first: its non-gravitational acceleration. Like Oumuamua before it, 3I Atlas did not follow a purely Newtonian trajectory. When plotted against the expected gravitational path influenced by the Sun and planets, it displayed small but consistent deviations. These deviations indicated that an additional force was acting upon it, something other than gravity. In most comets, such deviations are caused by jets of gas pushing the nucleus in the opposite direction, a natural reaction to sublimation. But 3I Atlas's acceleration was both too uniform and too directional to be explained by random jet activity. More perplexingly, it persisted even after the comet had begun to fragment and should have lost any structural integrity to produce sustained thrust. This pattern triggered a series of comparisons to Oumuamua, which had displayed a similar acceleration. In that case, scientists proposed that radiation pressure, the push from sunlight, could explain the phenomenon if Oumuamua were extremely thin, like a sheet or sail. That idea, while controversial, at least fit the data. For 3I Atlas, the same theory did not hold. The object was visibly disintegrating into diffuse clouds of dust, which would have absorbed sunlight rather than reflected it efficiently. Radiation pressure could not account for a steady acceleration in a disintegrating, irregularly shaped object. Yet the data was clear: 3I Atlas was speeding up in a direction that could not be reconciled with gravitational models. A few astronomers began exploring more speculative explanations. Some wondered whether magnetic interactions could play a role. Interstellar objects might retain residual magnetism from their birth environment, and as they encounter the heliosphere, the magnetic bubble of our solar wind forces could act upon them in unpredictable ways. Others speculated about charged particles interacting with the solar wind itself, creating minute electric fields that might alter trajectory. These hypotheses were grounded in known physics, but required conditions that were extreme and unlikely. To generate the observed acceleration, 3I Atlas would have needed a level of magnetization far beyond anything ever detected in natural bodies of similar composition. Meanwhile, the chemical data began revealing its own peculiarities. Spectral lines corresponding to carbon-based molecules appeared unusually strong, but the ratio between those molecules was inverted compared to known comets. Methane was scarce, while carbon monoxide and cyanogen were abundant. This imbalance hinted at an environment of formation very different from the early solar system. In some spectra, faint traces of complex organics appeared, molecules that resemble precursors to amino acids. These signals were faint and could easily have been artifacts of interference or data noise. Yet the possibility that 3I Atlas carried the molecular fingerprints of alien chemistry stirred excitement and unease in equal measure. There was another subtle anomaly in the timing of its fragmentation. Typically, comets begin to disintegrate gradually as they approach the inner solar system, their breakup events spaced irregularly as internal pressure builds. But 3I Atlas seemed to fracture at nearly precise intervals. When researchers plotted the timing of the fragmentations against its rotation period, a correlation emerged. The intervals corresponded almost exactly to integer multiples of its spin cycle. This implied that the object was structurally linked to its rotation, that the stresses triggering the fractures were periodic rather than random. It was as if each rotation applied strain to specific regions, gradually weakening them until they reached a breaking threshold, then resetting for the next cycle. Such mechanical synchronization is unusual in natural bodies. It suggested a form of internal symmetry or regular layering, a pattern, architecture that hinted at a history of orderly formation, rather than chaotic accretion. Adding to the mystery was the behavior of the dust trail left behind by the disintegrating nucleus. The trail's dispersion pattern did not follow the typical fan-like shape produced by solar radiation pressure. Instead, it appeared denser and more cohesive, as though the dust grains were bound together electrostatically or magnetically. Observations with polarimetric filters indicated a higher degree of polarization in the reflected light, consistent with elongated or metallic particles rather than the irregular silicate dust found in most comets. This discovery prompted some researchers to speculate that 3I Atlas's material composition might include exotic metal alloys or conductive minerals rarely found in natural objects. The implications of that possibility were staggering, as it would mean that interstellar processes could forge materials under conditions unlike anything in our solar nebula. Each anomaly deepened the enigma rather than resolving it. Every time one mystery seemed on the verge of being explained, another appeared. The data suggested that 3I Atlas was at once fragile and strangely durable, reactive yet stable, luminous yet cold. It refused to fit into any single category of celestial object. Scientists wrestled with the numbers, testing model after model, yet none could reconcile all the observed features simultaneously. The object was like a cosmic riddle, a whisper from another star system telling a story in a language we could almost but not quite understand. And as the last fragments of 3 Atlas faded into the darkness, leaving only the faint residue of its dust in solar orbit, the anomalies did not vanish. They lingered in the data archives, lines of numbers that refused to make sense. Subtle reminders that the universe still keeps secrets, even from those who dedicate their lives to deciphering it. When the first detailed datasets of 3I Atlas were compiled and shared across the global astronomical community, scientists from every major observatory began to pore over the numbers, searching for a cohesive explanation that could unify all the perplexing features this interstellar visitor had displayed. Every telescope, from the Hubble Space Telescope to the Pan-STARRS survey, had captured fragments of its behavior, and every image hinted at a new question. Its unpredictable light fluctuations, peculiar fragmentation, chemical asymmetry, and unaccountable acceleration demanded a theory, something bold enough to account for all of it. But as is often the case in astronomy, the data yielded not one theory, but many. Each emerged from a different school of thought, reflecting both the diversity and the creativity of the scientific imagination. What made this phase so fascinating was not that any single explanation stood out as definitive, but that every theory revealed something deeper about the limitations of human understanding. The first and most straightforward explanation came from the traditional camp, the idea that 3I Atlas was simply a highly fragile comet from another star system. According to this theory, the anomalies in brightness, acceleration, and chemistry were not mysterious at all, but rather the natural outcomes of material differences between comets formed in different stellar environments. In other words, 3 Atlas behaved oddly because it was odd, because it was made of ingredients we rarely see. The abundance of carbon monoxide and cyanogen, for instance, suggested it had formed in an environment far colder than the early solar system, perhaps on the outskirts of a dim red dwarf star. Such a frigid birthplace could have allowed the preservation of exotic ices that vaporized explosively when exposed to the warmth of our sun, producing irregular jets and asymmetrical forces. This could explain both the erratic brightness and the unsteady trajectory. The changing rotation rate might then be the result of internal collapse, as pressure pockets burst one by one, slowly altering its spin. This model was elegant in its simplicity, relying entirely on natural processes, but it also failed to explain the uniformity of the non-gravitational acceleration and the periodic fragmentation pattern, both of which seemed too ordered to be random. Another group proposed the rotational breakup hypothesis. In this theory, 3I Atlas was a fast spinner that tore itself apart through centrifugal force. Many small comets have been observed to disintegrate this way. As they spin faster and faster, the weak gravitational cohesion between their fragments gives way. The evidence for this lay in the timing of its fragmentation events, which seemed synchronized with its rotational period. However, the recorded spin rate did not appear fast enough to produce such structural failure, unless the object was extremely porous, like a clump of cosmic dust barely holding together. To test this, astrophysicists simulated the object's spin dynamics, inserting variables for porosity, density, and tensile strength. The results were mixed. Even at maximum fragility, the observed breakup could only be explained if the spin rate increased dramatically in a short span of time. What could have driven that sudden acceleration remained unclear. Sublimating gases might have acted as thrusters, but no corresponding jets were seen. Thus, while the rotational breakup theory explained the sequential fragmentation, it still left other questions unresolved. A third, more radical hypothesis took shape in the wake of 3I Atlas's anomalous acceleration. This theory extended the concept first proposed during the Oumuamua debates, that radiation pressure alone might have been responsible for the motion. But for that to work, 3I Atlas would need to have had a large surface area relative to its mass, perhaps shaped like a sheet or hollow structure, capable of catching sunlight much like a sail. This light sail model suggested that 3I Atlas might not be a natural body at all, but a fragment of artificial material, possibly debris from a technological civilization elsewhere in the galaxy. The notion was provocative and drew both enthusiasm and skepticism. Scientists are cautious when extraordinary claims arise, but even the skeptics admitted that the radiation pressure model fit the acceleration data better than outgassing models. However, the idea of it being an artificial object faced significant challenges. Its disintegration appeared too chaotic and too consistent with ice sublimation to suggest an engineered origin. No radio signals were detected emanating from it, and its spectral signature was rich in organic compounds typical of comets, not metals or synthetics. Still, the light sail hypothesis persisted in popular science discussions because it captured the public imagination and reminded researchers that our data might someday reveal something genuinely artificial in deep space. Another compelling line of reasoning focused on magnetohydrodinamism. This theory proposed that 3I Atlas might have carried an intrinsic magnetic field acquired during its formation, and that as it entered the heliosphere, the bubble of magnetic plasma emitted by the Sun experienced magnetic drag. Such interaction could, in principle, produce small but measurable accelerations that appear non-gravitational. The idea gained traction when models showed that under certain plasma conditions, charged dust grains could generate forces that mimic propulsion. Yet, for this to occur, the object would have needed to contain magnetically susceptible materials and hold a net charge across its surface. Neither of these properties could be confirmed with current data. Moreover, the predicted acceleration vector from magnetic drag did not align perfectly with the observed trajectory changes. The theory was elegant in physics, but fell short in precision. A subset of astrochemists explored another intriguing possibility, that the object's behavior resulted from exotic ice phase transitions. In this scenario, 3I Atlas was composed not of ordinary water ice, but of high-pressure crystalline forms of hydrogen or methane ices that had remained stable in the deep cold of interstellar space. As it approached the Sun, those materials would have transitioned to gaseous states explosively, releasing energy in bursts that could cause both fragmentation and non-gravitational thrust. Such transitions could also produce localized temperature drops and fluctuating albedo, accounting for the strange brightness patterns. The biggest challenge to this theory was the lack of direct spectroscopic evidence for those exotic ices. But given that the object's signal was faint and often obscured by dust, it remained possible that crucial chemical markers had been missed. If this theory were true, it would mean that interstellar comets could serve as natural laboratories for physics at extreme conditions. Ice forms that can't survive within our solar system but are common in the vast cold of interstellar space. Then, there was the fractal aggregate theory, which tried to reconcile the object's light reflection and density simultaneously. This model proposed that 3I Atlas was not a single compact nucleus, but rather a loose, sponge-like cluster of microscopic grains, a snowflake of cosmic proportions. Such aggregates could be incredibly light and porous, allowing sunlight to exert significant radiation pressure on them without requiring an artificial explanation. They would also fragment easily, consistent with the observed disintegration. Such a fragile configuration would have survived the journey unless held together by some cohesive electrostatic force. We don't fully understand. As the echoes of 3I Atlas fade into the silence of space, humanity is left staring into the deep black with a new awareness, a realization that what once seemed distant and unreachable has now brushed past our cosmic doorstep. Its journey through the solar system was brief, a passing moment in astronomical time, yet the questions it raised will linger for generations. It arrived as a comet, behaved like a mystery, and departed as a symbol of how much we still don't understand about the vast, interconnected fabric of the universe. From its strange internal structure and magnetic alignment to the haunting geometry of its disintegration. 3. Atlas forced us to look at the cosmos not as a backdrop of distant stars, but as a living, dynamic environment filled with travelers, messages, and remnants of forgotten systems. This discovery reminded us that the story of space is not written solely by the grand forces of galaxies and stars, but by the small, silent wanderers that drift between them. Every interstellar object that crosses our path carries with it fragments of history older than Earth itself, pieces of planets that once were, or perhaps could have been. In studying 3I Atlas, we found evidence of complexity where we expected simplicity, order within chaos, and traces of design where randomness should have prevailed. Whether that order was natural or something more, it tells us that the universe is governed by patterns we have only begun to decipher. Science, at its best, is not the pursuit of certainty, but the embrace of wonder. 3I Atlas reminded us that discovery is both thrilling and humbling, that each answer reveals a dozen new mysteries waiting in the dark. It showed that even a disintegrating fragment of ice and dust can ignite revolutions in physics, astronomy, and philosophy. It urged us to expand our vision, to build better instruments, faster missions, and deeper theories, not just to satisfy curiosity, but to understand our own place within the grand motion of the stars. For the United States and the world scientific community, the legacy of 3I Atlas is clear. Our exploration of interstellar space has only just begun. The next object will come, and when it does, we will be ready with sharper eyes, open minds, and the quiet courage to ask the questions that others fear to voice. Because every fragment that falls through our solar system is a messenger, and every messenger carries a story of cosmic time, written across the dust and light of the unknown. And so, as we drift into the quiet rhythm of the night, listening to the steady pulse of the stars, we are reminded of what 3I Atlas truly gave us. Not fear, but fascination. Not endings, but beginnings. A whispered reminder that somewhere, far beyond our react, the universe is still writing, still moving, still waiting to be understood, one mysterious traveler at a time.